Hello friends, in this lecture we will look at the motivation for studying digital communication, the objective and the expected course outcomes. We will also look at the list of text and reference books. So far we have seen the general block diagram of a communication system and that of a digital communication system. In a digital communication system's block diagram, we noted that a signal may be analog or digital at the source. It is essentially digital at the encoder output, whether it is source encoder or channel encoder, and it is essentially an analog signal at the output of a modulator. So, a digital communication system involves both analog as well as digital signals and as such hybrid in nature. Then what is the reason that a digital communication system is called digital? And that is the question we had raised in the previous lecture. In this lecture, we will try to look at that reason. So what is the essence of a digital communication system? In a digital communication, the information is represented by a bit stream, a stream of binary digits, say 1 0 1 0 0 1 0 1 1, something like that. Now, a 1 may be represented because for transmission of this signal, this bit stream, it must take a physical form, and therefore each bit or a collection of bits together must be represented by a physical voltage. In one particular scheme, we may represent 1 by a positive voltage and 0 by no voltage, or maybe by a negative voltage in a polar scheme. Say it is plus 5 volt and this minus 5 volt. So if you want to transmit this bit stream, it will be a succession of plus 5 volt, minus 5 volt, plus 5 volt, minus 5 volt, minus 5 volt, plus 5 volt, and so on of the fixed duration. This is duration, bit duration. Okay, so when we transmit these pulses one after another in a given time interval, what is required is to know whether the received signal is positive or negative in this particular scheme. So when the signal is transmitted in the channel, because of channel imperfections, the signal gets degraded. The pulse shape changes, the pulse amplitude changes, but at the receiving end, we are not interested in maintaining the exact shape of the pulse. We only require to know whether it is a positive pulse or a negative pulse, and that decision can be easily made, and a fresh pulse can be regenerated at the receiver or at a repeater station if it has to be transmitted to longer distances. We use repeaters at regular intervals so that we can keep regenerating pulses at regular intervals, and virtually the communication is possible over any feasible distance. This is not the case in analog communication, where the information resides in exactly shape of the pulse, and therefore if the pulse shape has distorted, has changed, there is no way to reconstruct the original pulse shape. If this can of course be done if there is no noise in the channel, but that is never the case. So in the presence of noise, the pulse shape and pulse amplitude is going to change, and an analog communication system cannot faithfully reproduce the original pulse. On the other hand, in digital communication system, we are not interested in the exact pulse shape, and therefore even if these degradations are there, we are not worried as long as we can regenerate the fresh pulse. Of course, there can still be some error if the amount of noise is so large that it takes possibly a negative voltage. Then we may assume it to be a negative pulse transmitted rather than a positive pulse transmitted, and in that case an error would occur. But the probability of that happening is far less, and therefore the amount of error that is incurred in digital communication is far less, and therefore the reliability is very high, which is a primary objective of digital communication. So in this example, we assume that a 1 is represented by a positive pulse and 0 by a negative pulse. We may go for other possible schemes in which we take a collection of bits, say 2 bits together. We take 1 and 0 together, 1 0 together, 0 1 together, and then of course we will have 4 possible combinations as 0 0, 0 1, 1 0 and 1 1. Now in this case we may choose 4 distinct symbols to represent these 4 possible bit pairs. Suppose 0 0 is represented by, say, a negative 5 volt, 0 1 is represented by a negative minus 3 volt, 1 0 is by positive 3 volt, and 1 1 by a positive 5 volt. Of course, the margin of error here will increase, but still will be able to make out which pulse was transmitted, a minus 5 volt or minus 3 volt or 3 volt or 5 volt, and accordingly we can reconstruct the bit stream and therefore make a good estimate of the transmitted signal. So whatever be the case, we take the bits individually or in pairs or in triples or 4 bits together and so on. In any case, the number of possible pulses we use to represent the signal is going to be finite. This we also call symbol in digital communication terminology. So the number of symbols are going to be finite, and it is this finiteness of the number of symbols that make the communication system a digital communication system. Because note that when the signal is transmitted through the channel, it is anyway an analog signal that can transmit through a physical medium. So this is the essence of digital communication system, and that makes our digital communication system a very robust, a rugged system, very much noise resistant. So a digital communication system's essence is that a transmitted pulse can be regenerated at a repeater or at the receiver. We are generating fresh pulses, and it is possible because the number of symbols or the number of possible pulse shapes in the symbol set used to represent the message are finite. For example, 2 symbols in a binary system or 4 symbols in a quaternary system. In modern communication techniques, suppose we are going for 16 QAM modulation or 64 QAM modulation, still this number 16 or 64 is finite, so we will have finite number of symbols, and it is this finiteness of the number of symbols used to represent the message that makes the communication digital. Remember, the symbols themselves are continuous time, continuous amplitude signals. That is, they are analog signals, and analog signals only can be transmitted through physical communications medium. Now, why to study digital communication? Well, it is a core course in electronics and communication engineering. More importantly, 2 primary objectives of communication, the reliability and the efficiency, they can be best achieved by digital communication system. Digital systems surpass analog communication systems in achieving them. Moreover, digital communication course forms a solid foundation for the follow-up courses in communications, such as wireless communications, cellular and mobile communication, advanced communication systems, and information theory and coding. The objective of this course is to provide a sound understanding of the basic principles of digital communication and the techniques to design and analyze digital communication systems. At the end of this course, the students are expected to develop the ability to explain digital communication techniques and problems in terms of block diagrams, digital communication technology, terminology, jargon, and any trade-off involved. Apply signal formatting techniques and principles such as sampling, quantization, pulse code modulation, delta modulation. These are all part of the encoder block, source encoder block that we have looked at in the block diagram under different situations in the analysis and design of digital communication systems. The third course outcome is to apply Gram-Schmidt orthonormalization procedure to obtain signal space representation for a set of linearly independent signals. As we proceed in this course, we will see that there is a very good analogy between signals and vectors that exist, and using that analogy, we can develop a procedure to represent symbols in the form of signal space representation or constellation diagrams, and using them we can, as given in course outcome 4, evaluate the performance of various fundamental digital baseband and bandpass transmission techniques in terms of the probability of error and spectral efficiency for AWGN channel model, where AWGN stands for additive wide Gaussian noise channel. By baseband, we mean that the original information is transmitted in the lower original frequency band, whereas band pass transmission implies that the signal is used to modulate a high frequency carrier for transmission. The fifth course outcome is the ability to develop the skill to determine the two fundamental limits in communications for simple cases. One, entropy for memoryless source, and the channel capacity for memoryless channels. And the meaning of these course outcomes will become clear as we proceed with the course. The textbook for this course is Digital Communication Systems by Simon Hekin or Communication Systems by Simon Hekin. Any of the two can be followed. A second reference textbook for the course is the Digital Communication by P.R. Rao. Some very good reference books are Digital Communications by Prokis and Salehi, Principles of Communication Systems by Top, Schilling and Saha, Modern Digital and Analog Communication Systems by Lathi and Ding, and the Shams series book it's good for problem solving. So thank you.